Howdy, I'm Diego Reyes,
Howdy, I'm Ricardo Rodriguez.
Howdy, my name is Mark Bettis.
and we'll be presenting our end of the semester project. This project is the autocorrecting automobile dynamic pendulum system. There you go. Can you see the next
So
slide?
first, we're going to go into a little overview about the project. So the autocorrecting automobile dynamic pendulum system, or vehicle pendulum, is an autocorrecting robot that stabilizes a fixed pendulum of mass by changing the acceleration of the vehicle in the direction that the pendulum is falling. So the main project objective or the goals of this project is to design and develop a vehicle that will house a pendulum as well as a controller that will stabilize the pendulum using motors to accelerate the vehicle. This project will allow us to gain a better understanding of control systems used for dynamic applications in robotics, which is a big deal, especially since many companies are gearing towards having fully automated systems, such as Tesla. If we take a look at the of how the Tesla cars are manufactured, everything is done through robots that are automated. So by doing a project where we are able to create an automated system, we're gaining a little bit of an understanding as to how these topics can be applied in an industry setting.
All right, this section of the lab will focus more on the software development to of this side, so we can connect it to our hardware. The first component we should focus on would be the potentiometer and how to convert it into radiance, so we can better understand, so our software can better understand at what position it is. Uh, so first we have to change the analog voltage signal to radiance, which will use the conditional equation seen here. The AI is analog input, and to multiply that value by 0.225, and then subtract the 139.5 only if the analog input times 0.225 is a negative value. However, if it's a positive value, we will just get the analog input times the 0.225 and multiply it times the pi divided by 180, so we can get radians. And that is as we can see over here, down here in the second figure, is what we do. We change it to a double type of integer, and we do a gain of 0.225 for the MATLAB simulation, and we do a summation, and the summation for the negative would be the 139.5 if it's a negative value, and then we just do another gain for a pi divided by 180. Yep. The one on the left side represents our analog input, and the one on the outside represents our radiance that our system will be seeing. All right. Uh, the second part of our components that we'll be looking at would be our MATLAB function. This function will allow us to actually configure the motors for them to be on or off. And these two motors are connected in such a way that they only have two configurations, upwards and not upwards, forward and backwards. And Y2 would be backwards and Y1 would be the configuration for forward. So if our U, which is our analog input, is configured as a positive value, we would first have to set to zeros the other output, PWM output, and then we can choose our Y1 as our positive PWM signal. And we do the same thing for when the U is less than zero, basically. And this configuration, this if conditional statement, represents a bang bang controller, or represents similar to a bang bang controller. Yeah. All right. The last configuration is to actually set them all, uh, set all the connectors up. So as we can see, Y1 would just be a pin output for PWM. Pin The Y2 would just be a pin output for PWM, but it would be two separates. One is forward, one is backwards. We have to get a 200 gain for the input, and the one is our analog input with the PID controller configuration already in set. So our PID controller in set, we use really uncommon characteristics. We use the 1,000 proportional value PID controller and integral value 1 and derivative value 1 and a filter coefficient of 100. And it was some pretty crazy values, but those are the ones we use for this project. And yeah, we used a 200 gain just to get a much faster PWM power power. So since the 255 is the maximum, if we get 200, it would just be 78% of the PWM available to the motors, which is already pretty strenuous to the small motors we're gonna be using. And I think that's it. That's all the software that we developed to actually go into conjunction with the hardware.
Okay, so I'm gonna be talking about the components that we used for the robot. So then for our microcontroller, we use an Arduino Mega 2560. This will serve as our like base of operations. This is where we will upload our program, and we will use our pinouts for to read the potentiometer and to read the input for the motors. So for the next component, we use as a L29 8N H bridge motor driver. This is what would drive our motors since our Arduino does not have the current or the voltage enough to power the motors individually. We'll be using this along with like an external power supply to power our motors. We'll also be using a gearbox assembly and wheels. So this will be connected to the motor, which will then and the gearbox will then turn the wheels, moving the vehicle. For our power supply, we're using a 9-volt power supply cable that will come from the outlet. It will plug into um, a switch that we have, and we have it wired to the motor driver. We're also using the 10K ohm linear potentiometer. This is what we'll be using on our pendulum system. Um, this we will be reading the input of the voltage or the in order to determine the position of the pendulum in order so we can know uh, what direction we need to turn the motors in. So this is going on. This is a list of things we did for hardware development. We first started by wiring the potentiometer and the motors. We used a soldering station to wire to wire three external wires to the potentiometer, which would be the power, the ground, and the wiper. And we also wired two wires for each inputs of the motors. So then when we started assembling, we first tested it without the full robot. So we just tested the motors and the microcontroller on its own, just to confirm that it was working correctly. We then prepared the robot base by assembling it together. When we received the robot base, it was in pieces, so we had to glue the gearbox to the motor base, fix the motor driver on the underside, fix the microcontroller, the Arduino, make sure it has a platform to rest on, and make sure everything was secure. So when it was moving, nothing would come free or anything else. Um, we also had to use a 3D printer to print our pendulum. We used Creo to design the pendulum model. Our pendulum is around 1 foot in length, and we're not sure about the mass. So continue on to next slide. This is more images of the completed vehicle. Oh, as you can see, we have I'm not sure what to call it. It's our pendulum system. So we use several stacks of cardboard in order to secure the pendulum to the car. So it will have a sturdy base, and we use hot glue and popsicle sticks and all sorts of things just to make it work. We were very limited on resources in the lab because we came in at the during break, and I think that's all.
Yep.
We're going to testing.
Once the program and the hardware configurations had been completed, we then moved on to the testing phase of the project's development. And the main regions for testing that were done were the placement of the components to allow for the best motion of the robotic vehicle, Other areas of testing included altering the values within the Simulink's proportional integral derivative, the PID controller, as well as altering the length of the pendulum that was being used for our project. So in terms of the placement of the hardware components on the chassis of the or the body of the robot, some of the main alterations that we made in the testing phase was determining the orientation of the microcontroller that we were placing on the body of the vehicle, just to ensure that the microcontroller's components, such as the power cords or anything like that, were not going to be interacting with the wheels. So we chose to put it on the side of the body where the two larger wheels were not going to be interacting with any of those components. Another area where we tested placing the hardware components was with the H bridge, which we actually mounted on the underside of the body, which allowed for the connections to the motors to be a little bit easier. Um, and one of the sort of problems that we encountered after we had already placed all the components on the body of the vehicle was that most of the heavy weighted objects are all on one side of the board. So it did cause the motion of the vehicle to not be as well as we wanted it since it was heavier on one side. So that was one portion of the testing. For the proportional integral derivative, the PID controller, we tested various values, and we saw that when we increased, I believe it was the proportional value to 1,000, we
Yes.
noticed that the car would move more precisely. So those the finalized values were are mentioned above in our lab report for the PID controller. And lastly, for the length of the pendulum, we initially made the length of the pendulum to be 1 foot, which is 12 inches. And we noticed that when we were testing it, that it didn't, the robot didn't move in the ways that we wanted it to. So we ultimately made the decision to cut it down to 3/4 of that length. So we took off a fourth of the length, and we saw like an increase in the productivity of the robot itself. So another alteration that we could make in the future is instead of having it to be a solid pendulum, we can maybe try hollowing it out to decrease the mass of the pendulum so that hopefully the robot would move better. But overall, the results of the project were that the overall function of the pendulum was practical, meaning it moved in the way we wanted it to based on our program that we developed, but some improvements can be made to increase the productivity of the system. Like I had mentioned, moving some of the weight to different areas of the robot so that the back wheels can have enough torque to compensate for the pendulum's movement, or hollowing out the pendulum, just different improvements that we can make so that the project can be better designed and work better. Next slide.
I'm showing a video, the proof of concept of our robot. So this is a short video. We will pick up the robot in the air and we will move the pendulum. So as we continue. Okay, so as we move the pendulum forward, the robot should accelerate forward to stabilize the pendulum. As the pendulum tips backwards, the robot should accelerate backwards to stabilize the pendulum. So that's the concept of our robot. This is how our stabilization works. This is our first trial of the robot. We're barely starting. Um, as you can see, it stays stable on its own, but then once we tap it when begin it loses stability.
Yep.
And here's a second trial. This is still the full length pendulum, so it can kind of stabilize, but then it just crashes into the computer due to like the wire pulling itself, the short wire that we have. And here is like the final presentation of our pendulum car. This is 3/4 length, which is the optimal length that we found out for the robot. So as you can see, it stables on its own. We had to carry the laptop just to avoid the restriction from the cable, but yeah, you can see the robot stabilizes on its own. These videos will be included when we submit this presentation if you want to see them in depth. All right, this is some of the issues that we faced. Here we were testing the pendulum, but then as you can see, like just due to the setup that we have, we don't have like an ex internal battery source, or these wires are too short. It restricts our entire project. In the future, improvements we would like to make will be like adding a additional power source, like onboard power source, and a way to store the code on the microprocessor itself, so it doesn't have to be connected to the computer.
Yep. As my good Aggie mentioned, Jacob, that some constraints that we saw was the external power line. We had to use the outlet to actually get the 9 volts that we required for the H bridge, and then which subsequently powered up the engines. And the other one was that it was connected directly to the computer because for the Simulink modeling, it was only available through direct connection through the whole process. So if we wanted to take that away, we would have to use maybe C programming to actually be able to download it and assemble by itself for the controller. Mark, go.
Some of the other constraints that we face was limited testing area. So this sort of goes hand in hand with the wired connections to the computer, since everything was so basically tightly squeezed into one testing area. Uh, the motion of the robotic vehicle was very limited. So it would perform better if it was on something a little bit longer, an infinitely long, uninterrupted stretch of road or stretch of like a table, somewhere where like the testing area is bigger so that the motion of the vehicle is basically unlimited. Another one of the constraints includes the torque of the motors. The motors that we were using were small motors that didn't provide enough torque to handle the weight capacity that we had on board of the body of the vehicle. So by increasing, by having bigger motors that have a more torque available, we'd be able to have a better, a robot that has better functionality.
And some of the future improvements that we would like to add, as mentioned before, like a battery pack that would be on board on the car, so it wouldn't have to rely on the external power source, which will increase the mobility of the robot. Another improvement would be to add higher power motors that will have enough torque to move the robot rapidly, with enough acceleration to stabilize the pendulum. And some concepts mentioned before was alternative software, such as like C or C++, where we can upload our program onto the board itself, so it can um, run on its own. It wouldn't have to be directly connected to the computer or anything else. And what a larger testing area would improve our would be another future improvement if we were to continue this project.
Uh, can I jump in?
Yes.
Another improvement would be the chassis itself. I think it was too limited and its like function, like too many holes, too many. It wasn't distributed properly. If we were to add like more stuff, like as Jacob mentioned, more battery packs or more torque for the motors, it would need more space, and we have to like actually distribute the weight perfectly, just in such a way that the motors won't be as limited. Yeah, better chassis basically.
And with that, we conclude our presentation. Thank you for watching. Anyone else have anything else to say? No? Well, thanks and giggle.
Thanks. Thanks, Ingo. Thank you, sir.
Thanks.